Welcome, everyone. This webinar today, the Advanced Tracer Interpretation at Utah Forge, provides new insights on completion and stimulation challenges for advanced geothermal systems. The series is brought to you by the GEODE consortium, which is led by Project Interspace and the Society of Petroleum Engineers, and is funded by the U.S. Department of Energy's Geothermal Technologies Office. My name is Deanna Morrison, and I'm your facilitator today. It's now my pleasure to welcome our moderator, Partho Giri. Partho is the Vice President of the Americas at RESMAN, overseeing the company's portfolio across the region. With a background in unconventional hydraulic fracturing operations, supply chain optimization, and field leadership, Partho has delivered results in fast-paced, high-pressure environments. His experience includes leading operations, implementing supply chain efficiencies, and managing large-scale field operations across North America. A graduate of Texas A&M University with a BS in chemical engineering, Partho combines technical expertise with a proven track record in operational excellence, process improvement, and team development. I'll turn it over to you now, Partho.
Hey, yeah, thanks for the intro there, Deanna. So I'd like to thank the U.S. Department of Energy for helping sponsor this event. And I'm now very, very pleased to introduce our speaker, Chris Fred. So Chris serves as the Stimulation Technical Director for RESMAN Energy Technology. He has more than 25 years of experience in the energy sector and is a subject matter expert in stimulation, completion, and technology integration. Chris has a unique techno-commercial background and a proven track record of delivering leading technologies and practical solutions. He's previously held a variety of senior technology leadership positions at Schlumberger, or SLB, including Technology Center Director and Global Business Development Manager. Chris earned his PhD degree in chemical engineering from the University of Michigan and holds more than 30 patents and 40 publications. So with that, Chris, you may begin and take it away.
Thanks, Partho. No, I appreciate everyone's time today to hear, I think what is an interesting story about fluid flow in the reservoir for enhanced geothermal systems. What you're about to see is based on a unique combination of tracers that's never been deployed in this manner before. And as a result, I think we're learning some new insights in how fluids flow in hydraulically fractured reservoirs. So with that, let's talk a little bit about EGS. I think a lot of people on this call are probably familiar with enhanced geothermal systems where we're taking lessons learned and techniques from oil and gas, specifically horizontal drilling and multi-stage fracturing, to create an enormous amount of surface area in the subsurface. The result of that is obviously a lot of area for heat transfer for efficient geothermal applications. To put the surface area in perspective, the bar graph at the bottom is showing you the surface area in square foot created by, in the first example, a horizontal well with a 5,000-foot lateral. That would generate about 9,000 square feet of surface area on the wellbore. If we were to add one hydraulic fracture to that system, that fracture itself has 270,000 square feet of surface area. So 30 times the surface area in one fracture compared to a 5,000-foot lateral. And then you think about multi-stage fracturing, an example here with 20 fractures along the length of that horizontal well brings us to over 5 million square feet of surface area, which would be equivalent to 600 of these horizontal laterals, or a well that's 3 million linear foot long. So again, fracturing provides a very efficient way to create a lot of surface area and hence drive the economic performance of EGS. So there's been a lot of innovation in this space, most notably from the Utah Forge and Fervo Energy projects. We've had the pleasure of working on Utah Forge, which is a frontier observatory for research in geothermal energy. And we'll talk about that work here today. And obviously, there's other players in this space as well, activities going on now by companies like Mazama, et cetera. So I think it's getting a lot of interest with the ability to really have an impact with bringing innovation from oil and gas into the geothermal space. Just want to take us back in time a little bit to talk about the evolution of thermal performance in EGS systems. And what you're seeing on the left-hand side of the screen is work done by Gringarten and coworkers in 1975. And they developed thermal decline curves to illustrate how two wells with fractures connecting them would perform over time to generate heat. Just to walk kind of through what we're talking about here, if we look down at the bottom, the top well is the producer. So we'd be injecting into the bottom well and then circulating through the fractures and back out the top well. If we look at this down the gun barrel view, when we hydraulically fracture, we're creating a hydraulic fracture geometry in this bluish gray color. We're pumping proppants along in that treatment to keep the fracture open after the treatment. And somewhere inside that hydraulic geometry is where the proppant will be placed. When we then put this into circulation for geothermal performance, we'll be circulating between the two wells somewhere inside that proppant area, illustrated by this turquoise area. So, we're creating lots of fractures. They're all going to have different surface areas. They're going to have different flow rates. So we're creating a heterogeneity of flow paths along the system. And if we look inside the Gringarten equation, the dimensionless time parameter here on the x-axis is a function of the flow rate per fracture and the area of that fracture that's available for heat transfer. So these are parameters that historically until now have not been measured directly from EGS projects. What's typically done is we would do a geothermal project. They would inject and circulate through the system. And after a few years of operation and cool down, they'd then be able to quantify the parameters in the model and assess the subsurface. What you're going to see today is through the use of tracers, we're getting a direct measure of the flow rate per fracture, and we're able to estimate the surface area per fracture as a result of about a 2-week test in the flow system. And that's allowed us to provide some economic estimates. So we can actually go in and look at the Gringarten solutions and provide estimates of the economic life of the project based on the data we have today. So we've accelerated the learning curve from 3 years to about 3 months. And you can also look at the details here. We can see differences on a stage-to-stage basis, which we can now go in and look at relative to the different completion and stimulation designs that they used along the length of the wellbore. And that's what we'll focus on our discussion on today is understanding what we're learning from the data and what are the ramifications of that big picture in terms of what the RESMAN team interprets as performance of the system that's in the ground today in Utah Forge. So let's talk about the Utah Forge setup. So in the top right corner, you're seeing a map or a photo of the Utah Forge area. You can see the projection of the wells in yellow and white. Below that are the trajectories of the two wells. These are deviated for reasons of basically doing gravity logging. The bottom hole static is 440 degrees Fahrenheit, or about 230 degrees Celsius. The history here is that in 2021, they drilled the 16A well, which is this blue well here at the bottom, the injection well. And then they did 3 hydraulically fractured stages in the toe of the 16A well and monitored the microseismic activity. They then drilled the 16B well in red through the cloud of microseismic activities and did circulation tests to evaluate that connectivity. The RESMAN team got involved in 2024 when the Utah Forge team added 8 additional hydraulic fracturing treatments along the length of the 16A well to make more connections between the two systems. And then we did circulation tests to evaluate that connectivity. So those fracturing stages, as well as the circulation tests, were traced to evaluate that subsurface system. As I mentioned, the Utah Forge team did a lot of changes in the system to try to understand what brings value and drives the performance of EGS systems. So in the various stages, the 8 stages that were completed in 2024, they varied the number of clusters per stage. And theoretically, each cluster should have a different hydraulic fracture that would connect the 2 wells. They varied the type of fracturing treatment used. So some of the stages were cross-linked CMHPG, so a highly viscous fluid. And some of the stages were slick water, just a friction reducer as the base fluid for fracturing. There were also challenges in the operations that changed the outcome of the treatments. So specifically in stages 6 and 7, due to the rock properties, they were unable to get sufficient rate for proppant transport with the wellhead pressure constraints. So stages 6 and 7 did not have proppant pumped into the treatment from the 16A well. When they were doing these treatments, the 16B well is cased and cemented. So there's fiber optic in the 16B well, and they're monitoring that for strain rate to understand where the fractures hit the 16B well. And after the fracturing of the A well, they then went in and perforated at those frac hit locations and did small frac treatments from the 16B to make sure that those two wells were connected in the frac system. So there were 5 stages in the 16B well. The first 4 were perforated and fractured per design. The last stage had a plug failure, so they only perforated but didn't fracture. So that means that we've got a few stages that have differences in proppant placement in the fractures, either from the 16A or the 16B, as well as the engineered changes in the clusters and the fluids. So we're going to look at all of those parameters and see how the tracer response varies depending on some of these changes. And we also integrated a natural fracture intensity log to help understand some of the trends we were seeing in the project. So to answer these questions, obviously we're using tracers that are unique inert tracers. We actually injected 30 chemical tracers in the Utah Forge project. Again, these are inert, they're non-hazardous and non-radioactive chemical tracers. These are water soluble. So we're adding water soluble tracers to each of the stages of the fracturing treatment, as well as pulses in some of the stages and during the circulation test. So we have a wide range of tracers that we're deploying in different technical mechanisms. In order to bring quantitative value to the tracer interpretation, we have about 5 different pillars of controls to ensure data quality and viability of the results. That includes precise control of the deployment of the tracer, the sampling, the analysis, etc. From the sampling perspective, we are sampling the produced fluids during flowback of the 16A well and the production from the 16B well during the circulation tests. And we'll show results from both of those data sets in this presentation. RESMAN's laboratory is based in Trondheim, Norway, which is essentially the Silicon Valley of the medical industry in Norway. So they've tapped into a lot of advanced biotech and medical industry technology and expertise to bring cutting edge advanced analytics into the analysis of samples. And that's enabled them to deliver parts per trillion resolution on the tracer concentrations. So with that enables a lot of advanced interpretations that you're going to see here today. And again, we're using this information to come back and answer these key questions and variability in the designs of the treatment. In order to qualify these tracers for geothermal applications, obviously there's a lot of work done before the project. This is just giving you a little bit of a snapshot. The top is laboratory thermal stability tests that were done. The RESMAN team screened about 60 different tracers, of which 30 were selected for the Utah Forge project. You can see here just a couple of examples of thermal stability tests over a temperature range of about 200 to 240 degrees C. You can see a couple of examples of tracers that passed versus some that failed the thermal stability tests. A wide range of tests were done there. I think the other one to highlight here is the reservoir pilots that were done during the operations in Utah Forge. And this involves co-injecting of multiple tracers together to ensure we get consistent results from the tracers to qualify them under the reservoir conditions. And this is just showing you a couple of examples of tracer performance from those co-injected tracer pilots. So with that intro on the kind of technology that we've deployed, let's talk about the solutions that we implemented. So what you're seeing here are 5 offerings that we can deliver with tracer technology. If we start first on the far left, this is stage contribution. And this is something you're probably pretty familiar with seeing, where we're just adding a tracer to the food and we're looking at yes or no, did that tracer come back during flowback in production. Generally, this isn't generally quantitative because it's often using tracers that are kind of cupped into the blenders and not necessarily metered into the system. So under those conditions, I would consider this a qualitative indication. Yes, no, the stage contributed. The ones in blue are all quantitative analysis, the colored boxes. The first one is a qualitative production log. What you're going to see in the raw results are basically a performance of the flow contribution per stage over time. And essentially every bottle that we're sampling on surface allows us to provide a production log. So it's basically a quantitative production log, or QPL, in a bottle. The second offering is fracture-driven interactions. And here we're looking at essentially the frac hits. And if you think about the oil and gas world, frac hits between wells may be good or bad. In the EGS world, it's exactly what we're looking for, right? We want the fractures to connect to make sure that we have communication across the flow system. So our FDI characterization involves assessing and quantifying the uniformity, the connectivity bias or pinch points between the various wells, and the durability of those connections over time. We also look at fracture characterization. Here we're adding pulses strategically to the stimulation treatment. And because we're changing the flow path while fracturing, those tracers take a different path in the reservoir. And by monitoring those moment responses, we can then assess information about the complexity of that flow path. Looks like we're having connection problems. Partho, can you confirm?
No, no connection problems.
Okay. All right. So with these tracer pulses, we can assess something about the complexity of the flow paths in the system. And then the last one is around flow efficiency. And this is when we're doing the circulation test or flowing between the 2 wells. We're adding tracers to quantify what's inside that turquoise area to understand the flow system and the area available for heat flux in the system. So we'll talk about a little bit about each of these as we go through the presentation today. The first one will focus on quantitative production log. And to start this, we'll just share with you the concentration versus production volume data here. These are showing the tracer responses with the vertical axis being concentration in parts per billion over the flowback or produced volume that we've done. Throughout the presentation, the data you see on the left-hand side of the screen will be flowback from the 16A well, and everything you see on the right-hand side of the screen will be from the production during the circulation test out of the 16B well. When you first look at this data, you see a lot of information, right? There's a couple points to highlight. One, we've detected all 30 tracers that we injected in the system. We continue to monitor all of those tracers, so they're all being detected and responding. You also see a lot of data on the screen. So obviously this is a science project where we're trying to learn. So we took a lot of additional samples and did a lot of additional analytics in order to make sure we had an accurate representation of the system. For commercial applications, we can do this with fewer data points, but we're showing you that, kind of a wealth of a rich data source here. The other point to highlight is that we're trying to do advanced interpretations that require an understanding of the shape of the tracer response, right? We're extracting information for how this changes over time. So again, that's another reason why we have a data-rich sample set here on the tracer response. So when you look at the data, we've got a couple of areas marked with arrows. You can see some spikes in the data. While we were flowing back the 16A well, they were perforated and fracturing the 16B well. So what you're seeing here are responses directly when operations were taking place in the 16B well. So this immediately tells us we have very good hydraulic communication between these wells. We're seeing a very quick response between the 2 systems. So one very good quick indication of a good strong fracture communication across the wells. The other thing you see, we've got in the circulation test, we did circulation tests in April, and then the well was shut down and shut in for a few months, and then another series of circulation tests were performed in August. And you can see that as we started up the treatment in August, there's a spike in the tracer response. The reason for this is that the fracture systems were flowing and circulating, and when we stopped pumping, the fractures closed a little bit and forced fluids out into the wellbore and forced tracer into the wellbore. So that's why we see a spike in the tracer response when we start back up. And then fresh water was injected to restart the circulation. So this black tracer was a circulation test pumped at the end, and you can see that that tracer was diluted and then comes back up as a result of the fresh water. So because of that, we're not going to share the details in terms of the transient that took place here today. We'll focus on the core part of the circulation tests in April and August. And it's also important to highlight that on the flowback data, the early part of the data was impacted by the sample location, as well as an overflow on the separator. So this data we haven't been using, as well as obviously there's a lot of operational activity taking place in the later part of flowback. So we focused in on the clean data sets in order to do the interpretation here today, and the volumes that we're using are illustrated in the data sets. So based on this, we can now start looking at the quantitative results. So the first thing we're sharing is the QPL, where we're plotting the percent flow contribution per stage. So the stages are along the x-axis, and they're also labeled with a number of clusters. So you can see this from flowback of the 16A well, as well as production during circulation in the 16B well. So you can see stage 9, for example, about 36% of the flow is coming out of that stage. You can see about 15% out of stage 7, and so on. And it's important to highlight, when you look at this plot, you're actually seeing about 45 separate production logs, because each of these lines represents a separate bottle. So we've got about 45 separate production logs illustrated here with undisturbed flow, right? We're just sampling the production on surface to quantify the flow contribution. We mentioned before that we didn't pump proppant in stages 6 and 7, and you can see that stage 6 is significantly underperforming relative to the other stages during flowback. So that makes sense given the lack of proppant there. The other thing you see is the two plots, whether it's from flowback or from circulation, look pretty consistent. So that's a remarkable consistency that also suggests we have very good hydraulic communication. In other words, it doesn't matter if we're flowing back towards the 16A or circulating towards the 16B. The flow distribution is fairly consistent across the stages, regardless of those two flow directions. So there's a second piece of information that says we have good hydraulic communication. So we can now dig into this data a little bit more. This is showing you the results on the circulation test from April. We're going to compress this data and add to it the August circulation tests, so you can see how the trends of those production logs change over time. We've added some additional colors here, so let me explain the differences. So the dark blue is from the April test, and that's a quantitative interpretation. The light blue is from the August test, and it's also quantitative. So the light blue is a direct relative contribution of the light blue stages. The stages in gray, we have lower confidence in their quantitative nature based on how the tracers are responding and diluting. So for example, stage 9 has significant dilution of the tracer. So we don't consider it quantitative at this point of the analysis. So the data that's not quantitative is in gray. So you can clearly see now, we have an assessment of the quantitative nature of the tracer, and then using that data accordingly based on our confidence in the nature of the response. So we mentioned the number of clusters are changing per stage. So let's go in and look at the quantitative production log versus the number of clusters per stage here in gray. And you can see there's actually a pretty consistent trend between the number of clusters in the stage and the flow contribution, as we would expect, right? The more clusters, the more fractures we should have connecting the two wells, and hence the more production flow through that stage. We add to this the volume of the treatment fluid in the bright blue and the mass of the proppant pumped in the stage. Those two bars are based on the total amount combining what was pumped from the 16A well, as well as what was pumped from the 16B well. So that's the total amount of fluid and proppant that should have entered that stage from either the A or the B well. And what we see is when we look at that bright blue bar for the volume of treatment fluid, it correlates very well with the quantitative production log, with the exception of stage 9, right? We see a pretty significant difference between those two on that stage. So to understand that more, we went and looked at the natural fracture intensity log, and that's shown here along the bottom. What you're seeing is the natural fracture intensity, or the number of swarm intensity of natural fractures, versus the lateral length along the wellbore. And if we focus in on stages 8 and 9 in the blue and green here at the bottom, you can see that stage 8 has about 8 natural fracture swarms along the length of that section, compared to stage 9, which has about 2 natural fracture swarms. Both of those stages have 8 clusters per stage. Right, so you can envision, we're putting 8 clusters in, hoping we get 8 hydraulic fractures propagating. You could envision with a lot more natural fractures, we probably get a lot of fractures propagating in stage 8, where potentially with some areas of the rock that didn't show natural fractures, maybe some of these stages don't grow so effectively in stage 9. What we're illustrating here in this cartoon with the lines is what we call cluster runaway. When we put 8 clusters per stage in the system, our intent is that all 8 of those clusters propagate a separate hydraulic fracture that connects to the other well. In reality, Mother Nature will control this system, and there'll be heterogeneity. And you can envision that some of those clusters don't grow a very dominant fracture, while that fluid that should have gone there will go in excess down another cluster, and this will be relatively large. This is what we're calling cluster runaway, where rather than having a nice uniform distribution, some of the clusters take excess fluid volume and get overstimulated relative to others that get understimulated. We built a metric to define this cluster runaway metric, and it's based on the ratio of the number of natural fracture swarms to the number of clusters per stage. And we're doing this to try to estimate the volume of excess fluid that went down that cluster that ran away. When we apply that ratio to stages 8 and 9, it turns out to be a factor of 1.6 for stage 9. And if we scale the treatment volume by that amount, it actually correlates fairly well with the trends we're seeing in the quantitative production log. So we believe the tracer response is telling us we have cluster runaway in stage 9. The question is, do we have other data to support this? So we ran a production log, a mechanical production log, during injection in the 16A well. And if we focus in on what's in the red box, we're looking at stage 9. So this is a mechanical production log showing the flow contribution during the injection in across stage 9 in the 16A well. And we see indeed 2 of the clusters did not take injectivity during this test, and 2 of the clusters took more of the injectivity than the average. So it does look like cluster runaway signature based on the mechanical production log. If we apply that same cluster runaway metric to this data, it also comes up to a factor of 1.6. So interesting consistency. We also have fiber optic strain data from the 16B well while we're fracturing. So what we're looking at in this plot is the strain rate in 16B as fractures are hitting the 16B well while we're fracturing the A. So when the fracture hits the B well, it turns into a strain response over time that you see as these red and bluish and yellowish streaks horizontally across the line. When we look at this at stage 8, you see about 8 hits that occurred in the 16B well compared to about 4 or 5. We now have 3 data sets that are consistent with a cluster runaway signature, with some of the stages dominating and some of the clusters dominating and not dominating in stage 9. So 3 data sets consistently telling us cluster runaway. And there's also indications verbally that the volume to first response from the strain measurements in stage 9 were actually pretty low. So again, indicating a cluster runaway type of scenario. So that's important to highlight because cluster runaway could be a short circuit between the systems and an EGS environment. So if this is happening, we want to understand what it does to the flow system. So 3 independent measurements now with tracer giving us a signature of cluster runaway. So we have a mechanical production log. Let's compare it directly to the quantitative production log. So this is the QPL from the tracer flowback in the 16A well. And we're comparing this now in yellow to the mechanical production log during injection. So we're not comparing apples to apples, but it's the same well at different points in time, one being flowback and one being injection. And you can see stages 9 and 10, the flow contribution looks the same, whether it's injection or production. You can see stage 7, where we didn't have proppant. We had good flowback, but then when we start to try to inject into it, the injectivity goes down. So obviously indicating some kind of inhibitants to flow and injectivity into the system without proppant. Should also highlight that the mechanical production log couldn't pass beyond stage 6. So you can see that this last yellow bar is everything from stage 6 and below. We have the resolution of those stages from the tracer data, and we just have the cumulative, right, from everything below that stage for the mechanical. A second mechanical production log was run later in the project in August, and this is overlaid now in orange. You can see again the tow stages makes sense, relatively speaking, compared to what we see. Looks like some fluid has redistributed from injecting in the stage 9 cluster into stage 10 over that time period. And we see that the 2 stages with no proppant have completely dropping off to 0 after August. So clearly we're losing injectivity potential at the perforations as a result of not having proppant in those 2 stages. So that's on the 16A well. We also want to make a comparison on the 16B well, but we have to do kind of a bit of a mapping exercise to do this. So let me explain the scenario. So the mechanical production logs are telling us the flow into or out of the perforations. The tracer data is telling us the fractures in the flow system that was swept. So we're looking at different information. In order to map those together, we're using fracture corridors that the Utah Forge team and Nubrex defined based on the strain rate in the 16B well. So when the fracture hits occurred in 16B, they drew polygons between where the frac hits were and the stage that was being treated at the time. So we're using this to map our quantitative production log of flow contribution to the perforations in the 16B well. So when we do that, we're going to map stages 3 through 6 to stage 1 in 16B. We're mapping stage 7 to stage 2 in 16B. We're mapping stage 8 to stage 4. And we're mapping stages 9 and 10 to stage 5 in the 16B well. And when we do that, we can build a cumulative flow contribution from the tracer QPL along the length of the wellbore, something we typically see from a mechanical log, right? And we can overlay a production log that was run on the 16B well in August over that. And if we focus in on the tow section, right, we had a limitation of the mechanical log to get beyond stage 3. So if we compare at this point in the wellbore, we see that about 36% of the flow for the mechanical log is coming from the tow, compared to about 32% from the tracer quantitative production log. So pretty consistent. So we have several mechanical production logs and the tracer log. We're going to put these all together now in a single table. And when we do that, we see that 36% and 32% from the mechanical and the tracer in the tow summarized here. And overall, you see all 4 of these measurements are showing a pretty consistent 70-30 mix. This includes the 2 measurements from the tracer QPL and mechanical from the 16B well, as well as the 2 mechanical injection mechanical logs from the 16A well. And those are both a 70-30 balance. So those 4 measurements are all pretty consistent in terms of the tow heel balance in this well. Just want to reemphasize the mechanical production logs are showing us entry and exit into the perforations, while the tracer is giving us the flow path that was traced. Because of that, we can now integrate this data and give us an impression of what the flow looks like in the system. When we integrate that data, this is what we see as the likely flow paths. So a couple of things to highlight. We're seeing a lot of contribution from stages 9 and 10 going directly to stage 5. That's important because we think there's a significant weakness in the rock fabric, natural fractures in that region that caused that cluster runaway and a dominant flow path there. You can also see that a portion of the fluid from stage 9 is actually entering the stage 10 perforations and still sweeping the fractures from stage 9. You can see stage 8 is taking its dominant path that we saw from the strain rates in microseismic. And then stage 6 and 7 do not have entry into the perforations based on the mechanical log. So the way to interpret that then is that we're getting a lot of flow in the perfs from toe down around stages 4 or 3 into the formation, and then it's flowing and connecting to the flow paths that were swept by the fracturing treatment originally. So whether that's a microannulus or connections through natural fractures, we don't know. Excuse me, but the point is that stages 6 and 7, those tracers are still being produced during circulation, meaning those flow paths created during fracturing are still in communication between the two wells, but the entry point is not the clusters per stage 6 and 7 based on the mechanical production log showing zero flow into those stages. So an interesting perspective on what we think the flow profiles look like in the system. So let's take this a little bit further in terms of the production profile on flowback. So this is the flowback QPL now normalized by the number of clusters per stage in the 16A well. And what's interesting to see here, with the exception of stage 6 that doesn't have proppant, the other stages have a relatively consistent contribution per stage of 3.7%. Actually, again, another indication, pretty good connection across all the stages, pretty consistent. The other thing you see here is there's differences in the slopes of those QPLs, right? We're measuring production logs over time. And what you see is it turns out the stages that have a positive slope all happen to be the stages that we pumped CMHPG cross-link fracturing fluids during the fracturing operations. Excuse me. All the other stages, they have a negative slope, and they happen to be the stages with slick water. So it starts to get us thinking, okay, what's going on? Why this difference? So you can immediately think, okay, CMHPG, cross-link fluid, maybe we're seeing the polymer break over time and cleaning up better. That could be why. But put it in perspective, this is over 400 degrees bottom hole static temperature. That fluid is going to break very quickly. So maybe yes, maybe no. You can also think maybe the slick water treatments, maybe not as good of a job with proppant transport. Maybe they aren't propped quite as well, and the fractures are slowly closing a little bit more in there, potentially. And the other scenarios, these are inclined wells, which means we've got a likelihood of some extra tortuosity in the near wellbore because of misalignment of the far field fracture planes with the complexity in the near wellbore. So that tortuosity creates extra pressure drop and resistance to flow that we can overcome better with a more viscous fluid to get better proppant transport and packing into that area. So this could also be an indication of maybe there's a difference in the near wellbore tortuosity in those systems. The actual mechanism, we don't know. We're just looking at, observations that there's a clear difference between the type of fluid that was used and how the production log is changing over time. So we'll come back to this with another data set in just a minute. But what I want to leave you with from the interpretation so far on the quantitative production log, we've seen a clear dominance of the number of clusters per stage, and we're seeing cluster runaway. And we're also seeing indications of differences in the types of fluids that were used in terms of how the stages are responding. So now we're going to go and we're going to look at fracture-driven interactions, and we're going to characterize what's between the wells. So the first thing we're going to look at is the uniformity. So this is the quantitative production log during circulation in the 16B well. It's now normalized by the number of clusters per stage. So we're seeing that on average, we're around 3.5% of the flow per cluster, plus or minus 1 standard deviation. That number is important to put in perspective. If we had perfect uniform distribution with the 27 fractures that could have propagated, we would have 3.7% flow per cluster. So we're at 3.5% plus or minus 1. So fairly uniform. But if we look at the bias of this, we see that we are field biased in terms of the fractures that are contributing. It's probably not a big surprise, right? So we're getting more flow contribution from the heel than from the toe on a per cluster basis. If we also think about the image we saw for the fracture corridors, we also saw that the 4 stages, 3R through 6, are all entering the 16B well through that single stage in cluster or stage 1 clusters in the 16B well. Right? So clear biasing of the flow here, if you will, slightly towards the heel section of the fractures. The other thing we look at is connectivity bias. And what you're looking at in the red and blue bars is a flux of tracer in the 2 directions, a flux towards the 16A well during flowback in blue versus the flux towards the 16A well in blue versus the flux towards the 16B well in red. The length of the bar is pointing in the direction of a flow restriction. So in the stage 6, you see that the red bar is long. This data is consistent with a flow restriction near the 16A well in stage 6, which makes sense given no proppant. If you look at the other stages, it's relatively balanced. It's relatively balanced between the 2 wells. In other words, we're not seeing a major constriction in flow in the rest of the system between the 2 wells. So on average, it's about a 51-49 split in terms of the connectivity bias in the system. So good result in terms of balance there. And the last thing we're showing here is the durability index. So this is basically saying how stable the systems were over the circulation test time. The data that falls below the line in the orange box are declining durability. So if we look at what's in that box, stages 6 and 7 with no proppant in the 16A well have durability that's declining over time, as does stage 9 where we saw the cluster runaway. We don't have a direct answer why stage 9 is declining, but you can envision that if we have cluster runaway, some of those clusters were understimulated, and the signature may be coming because those understimulated clusters are pinching off. That's just a theory, but it's consistent with the observation we're seeing in the durability index. The numbers we see above the line are more stable. And if we look at the fluids and the systems that are there, again, CMHPG shows up as more durable. Let me explain the data. The darker blue bars are from the April test, and the lighter blue are from the August test. So you can see that stage 8 was more durable across both of the circulation tests. Remember that some of the data was not quantitative in August, so those bars don't appear. For example, stage 9 and 10 are no longer quantitative, so we don't have the August bars here. So it's interesting to highlight CMHPG is above the bar and more stable. Slickwater was looking good in the first test, but it changed after the shut-in, and it's looking less durable in the second circulation test. There was actually a very big change before and after the shut-in for those stages. And we unfortunately don't have the August data because of the quantitative nature for stage 10, but it appeared to be more durable in the April test. And it's interesting to highlight because that stage 10 included a tail end of Omniprop, which is a lightweight proppant that should be better for proppant transport vertically between the 2 wells. So it's interesting to highlight that in this metric, CMHPG also shows up above the line. It's obviously below the line for stage 7 because there was no proppant in those 2 fluids, right? So this data tends to indicate that the fluids with better proppant transport, whether it's a viscous fluid or a lightweight proppant, those that are better for proppant transport appear to be more stable. So this is an interesting observation. We don't have proof of exactly what that mechanism is, but it's important to highlight that we are seeing differences in the durability index that seems to trend with the effectiveness of proppant transport. We've talked quite a bit about what we constructed and based on, what we pumped and what we got. Let's now go in and quantify what's inside that circulation area between the two wells. So we're going to look at flow efficiency. So to do that, we're focusing in now on the circulation test, injecting into the 16B well with water that includes pulses of tracer, and then producing out the 16B and monitoring the system. And what you're looking at here are the resonance time distributions for 2 of the pulses that pass through the system and recorded in the 16B well. So the 2 pulses you're seeing here overlay very nicely in the RTD response. These happen to be the last 2 tracer pulses that were pumped in the August circulation test. One was after around 20,000 barrels of fluid injected, and the other one was after around 60,000 barrels of fluid injected. So very different points in time, but both were measured at injection rate or a circulation rate of 10 barrels a minute. So at the same circulation rate, we're seeing a very consistent resonance time distribution response. And what we're highlighting here at the apex is 4,680 barrels. That volume from the RTD plot here is showing us the majority of the volume that was swept through the system from the dominant flow paths. Right, so that's essentially our circulation volume turquoise that we're trying to get to. So about 4,680 barrels across all frac stages is being circulated or swept between the two wells. So we want to put this in perspective. So to put this in perspective, we introduced a high-level metric, circulation volume efficiency. And we've defined this very simply as the volume of circulation at this apex, the 4,680 barrels, relative to the total volume of clean fluid that we pumped while fracturing from the combination of 16A and 16B. So the total frac fluid volume was 123,000 barrels. So it turns out this number is 4%. So why is this important? So it sounds small, it is small, and we need to understand this in context. These 2 wells are vertically stacked and they're about 300 feet apart. And we would expect that in that flow scenario, we get a pretty direct path between those 2 wells. It's very unlikely we inject into a 16B well and we sweep all the way to the bottom of the fracture around the tip and back up. That streamline is completely unrealistic to expect, right? So it makes sense that we have a small number here. So what is this telling us? It's telling us something about the impact of the well pattern, right? Here we have 2 vertically stacked wells that are close together because of the technical objectives being measured in the Utah Forge project. If we think about how people are doing this commercially, the Fervo team has moved the well into a wine rack pattern for commercial EGS performance. And in that scenario, the spacing of the well will change, and I would expect this efficiency to change. We also know if we look at this picture, we have a very big fracture relative to the positioning of the wells. So you could also envision for this scenario, we could have pumped much smaller fractures, gotten the same circulation volume, but a much different efficiency. So this high-level metric is telling us something about how well we've used the fracturing treatment for the given well pattern. And that's an important metric as we benchmark what we're doing in EGS from design to design. Okay, so that's a high-level metric to give us a footing on where we stand today. So that's 4,680 barrels. We have the QPL that we saw before. So we know how this is allocated per stage. So the turquoise bars you're seeing here is how this 4,680 barrels is represented across the various flow stages in the system. So we know the turquoise volume per stage in the system. And if we assume the number of clusters per stage, they're all taking an average amount of the fluid. This light turquoise bar represents the average circulation volume per cluster in the system. Okay, so we've got an interesting characterization now of the flow profile across the flow system. So embedded in this RTD is actually a lot more information. We'll just share a little bit more with you here. This is the interpretation looking at the flow components required to get that RTD response. What you're seeing is a fit of the data that requires at least 2 components to fit the data. I say at least because there could be there could be 27, there could be 50, right? But there's at least two dominant flow contributions in the system. There's the purple one that represents a fast path through the system, and there's the light blue one that represents a slower path through the system. And the volume, the flow contribution percent of those is 40-60, which is very interesting. If we go back and look at the QPL, that split is also 40-60 between stages 9 and 10 and everything else. So the QPL is measured using the stimulation tracers in the fracturing fluids. This RTD analysis is measured with a different tracer pumped as a pulse in the circulation. So completely independent measurements. It's interesting that they're consistent. We don't know if this is the exact matching. It's an interesting observation that they're consistent. So let's look at 9 and 10. They happen to be more planar fractures from the microseismic data compared to everything else that is more complex fracturing if we look at the microseismic performance. So it's an interesting observation how things look for stages 9 and 10 versus everything else, and that we could be having a fast flow path versus a slower path in this balance. This is one scenario of how to look at those two paths. There's lots of other ways to think about it. Another way to think about it is that there could be a fast path and a slow path in every single frac stage in the system. We don't know. This is one scenario, one way to look at it that compares interestingly to the microseismic data. All right, so that's an observation that doesn't appear anywhere else in the analysis. This is here just to give you a little more insights on the flow profile. So in this plot, we have this turquoise bar. Again, this is the volume of this area normalized by the number of clusters per stage. If we just zoom in now on this per cluster per stage, we can see how on average the flow volume per cluster changes. So let's understand this volume a little bit more. So let's go back to this 4,680 barrels, and let's put that 4,680 barrels in perspective to all the proppant we pumped in the system. We pumped 3 million pounds of proppant in the entire system. So 3 million pounds of proppant translates into a little over 3,000 barrels of proppant volume in this tan color. And if that proppant had 35% porosity, then the pore volume associated with that proppant would be 1,758 barrels for a bulk volume of 5,000. So what this is telling us is that the circulation volume is about 2 to 3 times higher than the pore volume of the proppant pack. The only way I can explain that is we don't have this much proppant in the flow path. Okay, so let's think about where the proppant may be. So to do that, we're going to go and look at this volume, and we're going to think about where the proppant is in the system for this given volume. So let's make an assumption. This is completely unrealistic as a reference point, but I want to do this to illustrate the best case scenario. And that would be, let's say we pumped buoyant lightweight proppant and it all went vertically above the 16A well, and all the proppant from 16B went down, so that 100% of the proppant we pumped in the system ends up in the turquoise area between the two wells. So completely unrealistic, but this is a reference point to tell us the bounds of this understanding, okay? So 100% of the proppant between the two wells. Now let's look at the plot. The dark blue at the bottom is coming from the proppant that we pumped from the 16A well. This is the pore volume associated with the proppant pumped from the 16A well if it had 35% porosity. And you can see that there's no dark blue bar in stages 6 and 7 because we pumped 0 proppant from those 2 stages in that 16A well. The dark blue bar at the top, that is the pore volume associated with the proppant that was pumped from the 16B well. So that's pore volume, again, associated assuming 35% porosity of that pack. The difference in the bright blue would be open channels if we have 35% pore volume in those 2 cases. So it's a significant number. The calculations are pretty straightforward. What you're looking at here, we're assuming 35% porosity, but we know there's no proppant in the 6 and 7 stage. We also, if you recall, we perforated the 16B stage 5, but we didn't put any proppant there. So again, no blue bar. In the toe section, stages 3 through 6 were all perforated and fractured from stage 1 in 16B. And we used the strain rate on the microseismic to allocate the percent of proppant allocated across those various stages. So that's why those bars are different for those 4. It's based on the strain rate response while fracturing in that well. So let's think about this in another way. The x-axis can be thought of as the 16A well. The top of the bar is the 16B well, and the bars are telling us everything in between those 2 wells that we're flowing through, okay? The percentages that we're showing on the curve is the effective porosity in the flow path. So the effective porosity is extremely high in stages 6 and 7 because we didn't pump much proppant, right? These are just flow channels with very little proppant in the system. But the average for the entire system is 59%. That's enormous. If we assume all of the proppant went above the 16A well and in the flow path, completely unrealistic assumption, that is a huge number. In reality, a lot of the proppant is below the 16B well. So this is a calculation assuming 22% of the proppant is in the flow path. We believe this is a realistic scenario, and I'll show you where the 22% comes in the next slide. So if 22% of the proppant is in the flow path between the 2 wells, then we're at 82% average porosity for the system. 82%. So how could that happen? So we all know that in the slickwater world, duning is a common scenario, right? We inject proppant into the treatment well, the sand settles in dunes at the bottom, meaning we have less proppant above the well. The other thing we know that happens is when we use low concentrations of proppant like we have in slickwater in an environment with natural fractures, we get proppant that hangs up around the asperities, and it leaves kind of open flow channels on a local level. And if you think about this from a macroscopic level, there was some work at Penn State University just modeling the duning scenario and what it looks like in the fracture while we're pumping, where we get a lot of proppant towards the bottom and a low concentration of proppant at the top. The results in, after fracture closure, these arches that form and open channels above the dune in this wedge or arch system above. In reality, we can explain this 82% by the combination of all 3 of these things happening. Right? So it's an interesting observation, and I think it's really important to think about for EGS. We want to make sure we contact as much rock as possible. We need to be conscious of the fact that in this system, we are dealing with a very high effective porosity in the flow path. So what does that mean for performance? We need to evaluate further. So let's take this a step further. We can measure the permeability of the system from the tracer data, and we can get to area. So let's first start with area. We're looking here at the volume again between the system. The only thing we're missing is the aperture of the fracture to take this to area. So if we make an assumption of a fracture aperture of 0.07 inches, we can calculate the surface area of the turquoise region. That 0.07 inches is coming from a RESFRAC publication where they simulated a fracture aperture of 0.12 inches between the wells in a Utah forge condition. We took a conservative number of 0.07, and the error bars you're seeing here represent a range of 0.05 to 0.1 inches. So we've done some sensitivity analysis on this unknown of the aperture. We're using 0.07 for our calculations, and you'll see error bars throughout the presentation that is the range for this unknown of 0.07 to 0.12. We now know the area calculated with an assumption of the aperture with an error bar on that range for heat flux across the entire system, each stage. So with an area, we can compare that to something. So we want to compare this now to get a ballpark. How well did we do? So we're comparing it now to the microseismic data. So we're introducing now a circulation area efficiency. So this is now the area that we've calculated for each of these stages. Again, a measured swept volume per circulation volume per stage with an assumed aperture of 0.07 is the area we're using for microseismic, or sorry, for tracer performance. That's a measured number with an estimate. And we're comparing that to the area from the microseismic cloud of events. And when we do that, the average for the entire system is about 22%. In other words, 22% of the microseismic area is being occupied by the circulation volume between the two wells. And you can see how that varies on a stage-to-stage basis. It's around 15% in stages 8 and 9. Interestingly, those had 8 clusters per stage. And it's up around 35% for stages 4 and 5 that only had 1 cluster per stage. So I look at this and say, oh, well, we've got better proppant transport in stages 4 and 5 because we have a controlled environment. And the benefit of that is more surface area coverage. It makes sense, right? So that immediately brings to mind a new optimum for EGS. In unconventional wells, we're very conscious of operational efficiency and getting as many clusters per stage as possible. And we're not so concerned about short circuits between 2 wells and the flow paths here because we want lots of area for oil production. In an EGS world, we're concerned about maximizing the area that we're covering. And it looks like with more control on how we place the proppant, we're getting more area coverage in the fracture. So this brings us to a nice opportunity to optimize the solution for EGS. And it'll be a different optimum than we have for oil and gas. We have an opportunity to learn and optimize the system here. So I mentioned we can measure the permeability from the system. So the average permeability of the flow path is 2 to 3 Darcy. What does 2 to 3 Darcy mean in a fracture system? Well, let's convert that to conductivity using the same 0.07 with the error bar of 0.05 to 0.12. When we do that, we get a conductivity on the order of 10 millidarcy feet. That's pretty consistent with what we see all the time in the oil and gas world for shale reservoirs. Kevin England and co-workers published a paper in 2000 that did a field study, and it came out to right around 10 millidarcy feet. So this is something that's common. If we compare this to a study I did in 2000 with Schlumberger, this is natural fracture conductivity experiments. So we're looking at the conductivity of a natural fractured core versus the effective closure stress. And you can see the Utah Forge conditions plotted on here. And it's interesting that we fall under the conditions where displaced fractures with no proppant or naturally fractured core with low concentrations of proppant like we're using here give a conductivity band consistent to what we just observed for Utah Forge and are also scenarios with open channel. So we have 3 cases now that are pointing towards open channel, very high effective porosity in the system to match all the various different data sets we have in the system. So let's try to pull all this data together now. So this is a very simple illustration, and my 8-year-old son had fun putting together this demo for me. So let me just explain what we're talking about. We're going to go back to fracture circulation volume. That is measured in Utah Forge with a tracer. We know that. So the fracture circulation volume is the volume of water we put in each of these glasses. So my son carefully measured the same fracture circulation volume in each glass. Consider the contents of the glass to be the flow path in the reservoir. So the first glass has 100% effective porosity with 4,680 barrels of circulation volume. The second glass has about 80% effective porosity and that same 4,680 barrels of circulation volume. And the last case is a 40% effective porosity with the same 4,680 barrels of swept volume. And what's important to highlight, you can think about this as the distance between the wells because the width of the glass didn't change. And the height is a geometry of the swept area that has changed. And as we reduce the effective porosity of the flow path for the same circulation volume, our area that is swept and available for heat transfer has increased. what does this mean from the data we have? Well, let's think about this. What's inside the glass, from a volume perspective, I don't care whether it's homogeneous, heterogeneous, channeling or not. If I put material in there to displace the flow, I get more surface area, regardless of what the path looks like inside the sand. The conductivity of what's in the sand very much depends on the size of the particles, on the channeling, on the homogeneity, et cetera, et cetera, et cetera. So those are parameters we can engineer. If we think about this from the big picture, we pumped 3 million pounds of proppant in both cases. In the 80% effective porosity case, a lot of our proppant is below the 16A well. It's not in the flow path. A smaller amount in the 40% effective would be outside of the flow path. This is important to highlight because everything that's outside of the flow path is completely irrelevant for the performance of EGS. That's important to highlight, right? This is completely irrelevant for the performance of EGS. It's something that happened because of the hydraulic fracturing treatment design we did. This is what matters for EGS. If we think about conventional fracturing design, we typically think in the brown dashed box. We're thinking about the entire fracture that's propped. That's our mindset, that's our perspective, that's our frame of reference. For EGS, I believe we need to be inside the turquoise box. I believe we need to change our frame of reference to the flow area. So the key message I really want to leave the audience with is we need to think not outside the box, but we need to think in a different box to optimize EGS. We need to be inside the circulation volume, and we need to optimize what's in here for the performance we need for an EGS system. So we go back to where we started. So we started with the Green-Garten equation. And remember the thermal decline curves where we hadn't measured the flow rate and the area before. Obviously, we can get the flow rate from mechanical production logs, but there hasn't been a direct measure of the area of an EGS system. So we just showed you the QPL. It's basically flow per fracture stage in the system. And we showed you the area on the fracture system on a per stage and a per cluster basis. So we now have measured those parameters directly after about a 2-week circulation test in the field. And from that, we can get the economics of the system. We can estimate the economic life of the project if we assume a target with a 20% dimensionless temperature on here. These are the numbers we see with an average effective economic life of 4.6 years. And you can see what's important to highlight, there's differences on a stage-to-stage basis. Stages 9 and 10 have about 3.5 year effective life. Stage 6 is also pretty low. You can see the best stages are actually stages 4 and 5, where we had a single cluster per stage and better proppant placement. So very important to highlight, these are things we can engineer. If we understand what's driving economic success for EGS, we can engineer a solution today without waiting for 3 years for thermal decline to understand what worked and what didn't and change a well. So we've just accelerated the learning curve by about 3 years. We've got error bars on this, right? We talked about the 0.07 to the 0.12 aperture range. We also talked about 100% versus 22% of proppant in the flow path. And we saw the picture of the glass that illustrated how important that was. If we assumed 40% of the proppant was in the flow path, it would look like this. We gain about a year of economic life if there was 40% of the proppant in the flow path. So we've done lots of sensitivity analysis on the various parameters. So we have a very good understanding of what's controlling the overall system response and where we think we can tweak results if we are thinking inside the turquoise box. So what do we take away if we think that way? I see 2 key challenges from a completion and stimulation perspective for EGS commercial success. The first is that we saw ineffective fracture geometry in stage 9 with what we see as cluster runaway. That's a fracture geometry that isn't contributing to the heat transfer effectively in the near wellbore. That can lead to short circuits and or a waste of the treatment volume that we injected. The second problem is ineffective fracture conductivity. Inside this turquoise area, we have an enormous effective porosity, right? That's not ideal for surface area contact. Both of those challenges impact the balance between the flow rate and the surface area in the Green-Garten equation. Both of those impact the economics. The mechanism that caused the disruption is different, and hence the mitigation measures we use to address item 1 or item 2 is different. And there's a wealth of things we do in the oil and gas industry to mitigate these effects. These are things we can engineer solutions to in the oil and gas world that can easily be translated to EGS. So let's go back and think, how did we do relative to the questions? So we looked at the quantitative production log. We saw clear impact on the number of clusters per stage, which is obvious. And we saw a very clear impact from cluster runaway impacting the flow profile. When we saw that both by looking at the flowback and by looking at the production during circulation on the 16B. We looked at what was in between the two wells with fracture-driven characterization. We saw the uniformity was pretty good, 3.5% plus or minus 1, with some bias towards the heel. We saw good balance between the 16A and 16B for connectivity. And importantly, we saw that the durability was declining, particularly for stages without proppant. And it looks like stages with good proppant transport are more stable. That is the trend we observe. That's something I think needs a lot more evaluation. The circulation efficiency, we've estimated a range between 4 and 22%, right? Somewhere in that range. Obviously, with the pattern of well spacing and the frac size for the science project in Utah Forge has a specific result, and when we go commercial, I expect that to change. But it's important to highlight those numbers are representative of what we have in Utah Forge today, and there's lots of things we can do from an engineering perspective to change that. We had a circulation volume of 4,680 barrels, and again, we saw those two distinct resonance time distribution components, one fast, one slow, that seems to correlate interestingly with the microseismic response. If you take anything away from this presentation, I think the most important one is right here. There is 60% as a minimum effective open porosity in the flow path. That is enormous. That's something we need to think about very carefully and whether that's good or bad for the operations we have. And I believe that is not anywhere near the optimum for the EGS performance. We saw an average system permeability of 2 to 3 Darcy, equates to on an order of 10 millidarcy feet with that 0.07 inch aperture. We didn't talk about this today for interest of time, but we also looked at fracture characterization using something we call tracer type curve. This is in the piloting phase, and we're happy to do more of this with different operating partners. But the interpretation of this also showed us planar type of fracture structure with local channeling type of flow path. So we have 3 independent measurements that are pointing to open channels in the flow path. And then finally, we saw that we solved Green-Garten's equation, right, from 1975. So 50 years later, we now have flow rate and circulation area quantified during a very short circulation test that can serve as the basis for optimizing completion and stimulation in EGS. And to put all of this in perspective, right, we've done quite a few answer products here, right? These are different tracer solutions, the combination of which has never been deployed before in the world. This is a direct measure of mass transport in the reservoir. There's no other way to measure mass transport. So that combination of 5 unique tracer technologies provides a very first look at some unique answer products out of this. And there's about 20 different things that we looked at that help quantify completion and stimulation design and serve as a basis for well optimization. And I want to emphasize that all of these things we showed today from an EGS perspective, they're applicable to any hydraulically fractured reservoir, whether it's a tight gas, a tight oil, or an unconventional play. We can apply the same workflows to any hydraulically fractured well. So with that, I just want to leave everyone with kind of a high level thought, right? The optimum approach for EGS will not be the same as for oil and gas. There's lots of things to balance. We've got operational efficiency versus the risk of cluster runaway. What's the number of clusters per stage that makes the most sense? We've got fracture conductivity versus parasitic losses during circulation. That directly impacts flow area and durability. And we have the ability to prevent or mitigate the challenges we see versus dealing with it and drilling new wells to offset it. And that has economic ramifications. Oil and gas tends to focus on drilling wells and operational efficiency. I believe for EGS, we need to focus across the diagonal here in the turquoise color. Think in a different box. The success of EGS will certainly leverage oil and gas lessons learned. I think we will be very successful, but we have to be focusing on a different well requirement in EGS. So with that, I'd like to thank the Department of Energy for the funding that supported this work, and also John McLennan and Kevin England for a lot of very useful discussions on the completion and stimulation aspects of the project. So with that, I thank everyone for their time and happy to answer questions. And if we don't have time to get through all the questions, feel free to email myself or Partho Guri as we go forward. Thank you.
So yeah, now we'll just we'll open up the floor for the questions that we have. Urge everyone to, if you haven't already submitted your questions, but if you click on the Q&A button at the bottom of your screen to send in questions. So the first one we have here is from Dimitri P. Hello, Chris. Question about slide 26. Stage 9, more planar frac than others, has lower flow frac surface area than the other stages. Does this mean that there is a higher chance to get higher surface flow area with complex fractures?
Yeah, interesting question. So when we think about oil and gas production, we want lots of surface area that connects back to the well. And by producing, we're creating a pressure drop that pulls on all the natural fractures that are connected. In the EGS world, it only circulates if it connects between the two wells. So all of that connectivity and fracture complexity would be good if that complexity connects to the 16B well. So I can't answer your question, but my gut feeling is that connectivity that complexity probably isn't helping us very much in the EGS world, because there's probably a lot of dead ends in the system. That's my impression.
Okay, we got another question, anonymous. Could you please explain a bit more about how the average economic life per fracture was calculated from tracer interpretation in Green-Garden?
Yeah, so the key unknown in Green-Garden is the flow rate per fracture and the surface area per fracture. So we get the flow rate per fracture directly from the tracer QPL. That's a direct measurement from the unique tracers that were in the fracturing fluids. And the surface area per fracture, that is coming from the volume per fracture and our assumption on the aperture that we interpreted from the circulation test, from the sweep, from the circulation test and that Apex 4,680 barrels. So we integrated two measurements from the project. We have the tracers in the fracturing treatment that was integrated with the tracers in the circulation test to give us the flow rate and the area per fracture in the system. Keeping in mind that we don't know the aperture, we assumed that based on the publication by ResFrac with an error bar on that range. All the other numbers in Green-Garden are known, right? It's density, thermal capacity, all those other parameters are known in the Green-Garden.
Awesome. So we got one from Ed S. Hi, Chris. Very interesting talk. It'd be interesting to repeat your analysis on a site where producer and injector flow paths were located horizontal relative to each other rather than vertically, presuming the percent calcs and alluding to stage 25 would look a lot different. Any comments there?
Yeah, I completely agree with you. So, no one else has done this type of analysis, right? The data doesn't exist to look at this elsewhere. But anecdotally, I'm hearing information from other projects in a wine rack type of pattern. The results sound similar to what we've seen here, but we don't have a direct measure. So absolutely right. Completely agree with you, Eddie. We would love to see this result in a wine rack or different well pattern alignment.
And then we've got two questions from Greg. So I'll post the first. I'll ask the first one and then the second one. Great presentation. Thanks, Chris. You described stages 4 and 5 as having the best proppant placement, yet these stages had an extremely complicated flow path, if I remember right. Thoughts?
Yeah, stages 4 and 5 were in the toe, and when they were fractured, the strain monitoring on the 16B well actually showed a fairly direct path between the 16A and the 16B. So that it looks like a relatively straight path from our interpretation. Obviously, we don't know the complexity in the detail, right? So it actually looks like a decent flow connection. The point to highlight there is fewer clusters per stage. One cluster per stage eliminates the uncertainty that Mother Nature has about how much proppant and how much fluid goes in the different clusters. So we know what went in the cluster in 4 and 5. So it looks like that control brought us much closer to the engineered objective and hence better results.
And then his second question, given what you've learned from your analysis, what are your thoughts on well placement? That is vertically stacked wine rack or placement in horizontal plane likely to give the best performance?
Yeah, absolutely. So the well setup for Utah Forge was done to make sure that the two wells were definitely connected by the hydraulic fracture. That was the objective. They wanted to make sure that they didn't miss the fracture with the 16B well. Remember, they drilled the 16A, fractured it, and then drilled the B well through the cloud of the 16A. So the well positioning was based on that strategy to make sure the connections existed. That was the primary importance. For commercial production, I completely agree. We need to be looking at wine rack and much larger well spacing, and the economics will drive that, right? It's the economic decision about the size of the fracs, the surface area we can create, and the number of wells it takes to generate the heat production required. But yeah, I think wine rack pattern is the appropriate strategy.
Okay, I actually have a question. So what we can come to appreciate about Utah Forge is that they are really about the sciences of understanding the subsurface and really chasing after the unknown, right? So as this project continues to move forward and the Utah Forge team continues to think about the next STIM campaign, what are some things that you think that they should be thoughtful and intentional about the design perspective when placing the next STIMs?
Yeah, so a lot of things to think about. I think if we just look at what's going on in oil and gas today, and what do we know and what can we control. So there's been a lot of work done on frac hits and oil and gas and the volume of first response. I think it'd be very interesting to look at volume of first response as maybe an indicator to say stop pumping from the injector well if we see a low volume of first response, not to overstimulate and create short circuits in the system. Prevention is better than the cure. The second thing is, we're seeing differences between cross-linked fluids and slick water. Is that because of tortuosity in the near wellbore or better proppant transport? Maybe both. So I think there's lots of things that can be done to further explore that. But yeah, I think thinking in a different box is the answer. We shouldn't get stuck in our conventional mindset from oil and gas and what makes a shale oil or gas well work. We need to think about what's inside that turquoise area and how to optimize that. And it's a very different objective than oil and gas.
No, thank you for that. Got another one here from someone anonymous. Since you spoke about positive and negative slope on the flow contribution per cluster, is there a conclusion on which aspect may be more beneficial for heat transfer when it comes to slick water versus cross-link polymers?
So if we think about oil and gas, slick water is there because it's cheap, it's easy. Operationally, we can move fast, and we're in a scenario where we have proppant settling and the proppant doesn't matter. If we think about EGS, conductivity matters because we're concerned about parasitic losses. I I think the benefits we're going to see, and I think it really requires shifting the mindset in the fracturing fluids, and high temperature fluids are tough to find, right? There's a few out there. But better proppant transport, I think, is a key thing. And we all know that proppant transport with slick water isn't very effective. Interesting to see that the omniprop stage looked better. So yeah, I guess if we go back to kind of the question, my gut feeling is proppant transport is important. Let's go back to the basics on proppant transport and think about what we can do in a 440-degree well to get better proppant transport in the system.
Awesome. Well, if anyone else got any other questions out there, the queue is open. Yeah, I'm not seeing any additional questions come through. So, Deanna, I'm going to hand it over to you. We got about 5 minutes left, and defer to your judgment here.
Oh, we got one more real quick.
Oh, we got one more. Okay, I like this. Are there additional tracers, data from Quantum Pro nanoparticles? Have you integrated those data yet?
Yeah, there's additional data. I know there's some work being done to provide some additional updates on that interpretation. We haven't integrated that data. I believe it's telling us a different measurement. I think we just have to wait to see the final interpretation to get that.
All right, now I'll take it over. Thank you, Partho and Chris, so much. Great presentation. Thank you, everyone, for attending and participating in today's webinar. Hope you have a wonderful day.
Thank you.
Thank you.